All right, so we're going to talk about the last couple of sections in Chapter 18. The first section is going to be electric field energy. When we first began talking about capacitors, I mentioned that capacitors store both electric energy and electric charge. We've talked about how much electric charge they can store. We use the relationship that the capacitance is equal to Q over V. So a particular capacitor at a particular voltage is capable of storing a certain amount of electric charge. They also store electric energy. They do this because the oppositely charged plates are attracted to one another. This is analogous to having a stretched spring. If I stretch a spring, the two ends of the spring are attracted and it wants to go back to its original shape. If I load up a bunch of charge on a capacitor, those two plates are attracted to each other and they want to collapse in on one another. The formula for the energy may or may not be obvious, but we'll look at it like this. The amount of work done, remember earlier we had this formula, so it looks like the work done in charging a capacitor should be QV. But there's a big but, and the but is that the voltage is increasing as Q is added. In other words, this isn't the situation where we have a constant voltage or a constant charge. So the work done in moving this charge is different. At Q equals 0, V is equal to 0. When Q is equal to Q final, I'm just kind of making this number up, V is going to be equal to V final. That makes sense. So what we can think about is the average voltage would be this final voltage divided by 2. We're going to call that V over 2. We also know that the charge is going to be equal to the product of C times V. So I end up with a formula that says the work done in charging a capacitor is 1/2 CV squared. That's the amount of work done in charging a capacitor. As a result of that work, the potential energy stored in the capacitor is also equal to 1/2 CV squared. Just like the amount of work in picking up a heavy box and setting it on a shelf is mgh, and the amount of potential energy that you gave that box is mgh. This is more like a spring though, because as you stretch a spring, it takes more and more force, and we end up getting that formula that potential energy stored in a spring is 1/2 kx squared. as we add more and more charge, the voltage keeps increasing, and we get this one. All right, let's look at an example. Our example says that we have two capacitors, C1, which is an 8 microfarad capacitor. It's connected to a voltage supply, V0, which is 120 volts. They want us to find the charge on the capacitor Q and the energy stored. And of course, stored energy is U. So here's our picture. We have one capacitor. There it is, C1. And we have 120 volts potential difference between this point and this point. So our basic formula says C is equal to the ratio of Q over V. So our charge is C times V. So I have 8.0 microfarads times 120 volts. If I multiply 8 times 120, I'm going to get 960. I still have the micro, that's 10 to the negative 6 microcoulombs. So that's Q. The energy stored, 1/2 CV squared. This time I am going to have to put this in an SI unit because I want to get the energies in joules. I don't want to leave the micro hanging around. So I'm going to say 8.0 times 10 to the negative 6 for capacitance and 120 volts squared. I put that in and I find out that the energy stored is 0.058 joules. So pretty easy so far. For the second part of this problem, it says, without any loss of charge, V0 is removed. Remember, that's this 120 volt supply here. And replaced with C2. So we're going to replace it with a second capacitor. The second capacitor is 4.0 microfarads. That is initially uncharged. After the charge redistributes, find Q and V for both capacitors. Then find the total energy stored. All right, so this is kind of different. We want to think really carefully. So we're going to take this voltage supply off, and we're going to put a second capacitor in. So here's C2. We know that C2 is 4.0 microfarads. Here's C1. C1 was 8 microfarads. And so our picture looks like this. Here's the first capacitor. Here's the second capacitor. And they're all connected. Now, we really have to understand some things about the problem. Let's point, I'm going to put 2 points. I'm going to put a point here and here, simply because those were the 2 points we had here and here. Here's what I know. I know the voltage across C2 has to be exactly the same as the voltage across C1. The potential from here to here, going this way, has to be the same as the potential from here to here. If I wanted to, I could have put those 2 dots right here. There's the same voltage difference from here to here, no matter which capacitor we're thinking about. These 2 capacitors are in parallel with one another in that sense. We know that the voltage across one has to equal the voltage across the second one. The other thing we know is when we had this, if we go up here, we had a charge of positive Q and we had a charge of negative Q. We worked that out and we found out that that charge was 960 microcoulombs. All right, what's going to happen if I put in an uncharged capacitor? If I have positive charge here and negative charge here, some of that charge is going to flow this way. Some of these negative electrons are going to flow. Charge will redistribute, remember, like charges, until you're going to end up positively charged here and positively charged here. We know that the total amount of charge on this plate was 960 microcoulombs. When that charge redistributes over 2 capacitors, the total will still be 960. So we know Q1 plus Q2 has to be 960 microcoulombs. We cannot create or destroy charge. We can only redistribute it. So if the total charge on the first capacitor was 960 microcoulombs on each plate, then when we get done, we still have to have a total of 960 microcoulombs of positive charge on the 2 positive plates and a negative 960, because the negative plate was, of course, negative 960. A total of a negative 960 on the 2 negative plates. If we use this fact that V1 is equal to V2, the voltage can be found using Q over C. So Q1 over C1, that would be the voltage on C1 right here, has to equal Q2 over C2. If I solve this equation, I get that Q2 is 960 minus Q1. I can fill in everything and only have one thing to solve for. Q1 over C1. C1, you'll recall, was 8 microfarads, equals Q2, which is 960 minus Q1, over 4 microfarads. If I cross multiply to solve this, it's pretty easy. I get 4Q1 equals 8 times 960 is 7,680 minus 8Q1. So 12Q1, left off the 1 there, equals 7,680. Q1 comes out to be 640 microcoulombs. Q2 then will have to be 320 microcoulombs. Let's think about this result. First of all, there's two really important things. This, of course, I got the 320 by saying 960 minus 640. This obviously adds to 960 microcoulombs, so we didn't create or destroy any charge. But the other important thing, if we look here, is C1 is twice as big, has twice the capacitance as C2. 8 microfarads compared to 4. It makes sense. If you have twice the capacitance, then you will store twice the charge at the same voltage. So at a particular voltage, we can see that Q1 is storing twice as much charge. So we've answered the first question. After the charge redistributes, Q1 is going to have 640 microcoulombs and Q2 only 320. We almost could have reasoned that out. If we have a total of 960 microcoulombs, the capacitor that is twice as big as the other capacitor has to have a charge twice as big as the other capacitor. The voltage can be found using V1 equals Q1 over C1. So 640 microcoulombs over 8 microfarads. Those micros are going to cancel out now. 640 divided by 8 is 80 volts. If I double check that and I see what the voltage is for the second capacitor, well, 320 microcoulombs over 4 microfarads is also 80 volts. Well, that makes perfect sense. Remember, our premise at the very beginning is these two have to be have the same voltage across them. The voltage difference from here to here has to be the same for both of them. It wouldn't make sense. It's like thinking of height. You can't say, oh, well, if you go up this way, this point is 10 feet higher than here. But if you go up this way, it's going to be 20 feet higher. Now, no matter which way you get to the top, that difference in height would be the same. That's an 80 volt potential difference. Finally, it's easy to calculate the amount of energy stored. The first capacitor stores 1/2 CV squared, so 1/2 8 times 10 to the negative 6 farads, that's 8 microfarads, times 80 volts squared, and we get a total energy of 0.0256 joules. The second capacitor stores 1/2 4 times 10 to the negative 6 times 80 squared, and that gives us 0.0128 joules, half as much, so that the total energy, if we add those two together, is actually only 0.038 joules. So we did not actually increase the amount of energy stored when we did that. As the potential difference between the plates went down, remember initially we had a potential difference of 120 volts, it went down to 80 volts. You can think of that almost being like relaxing the amount of stored energy. The amount of energy depends on the square of that voltage. So by decreasing the voltage, we decrease the amount of energy that we had stored. Okay, the last topic in Chapter 18 is about dielectrics. Most capacitors have a non-conducting material. Another word for a non-conducting material would be an insulator. Or another word is a dielectric. So a dielectric is a non-conducting material between the plates. I think I talked about this when I first introduced the idea of a parallel plate capacitor, so that you have a situation where you have a conductor, then you put a layer of your dielectric material, your non-conducting material, then you have another layer of conductor, and then you put another layer of your non-conducting material. If we were going to make a homemade capacitor, we could do it with saran wrap and aluminum foil. So we have conductor, those are our plates. Those are where we're going to hold this, that's where we're going to store the charge. And then we have the dielectric material, the insulator. Typically, the thin sheets are rolled up like a jelly roll to be compact. So think of just putting those in a nice flat, making sure you have plenty of dielectric so that the two conductors cannot touch, those conducting plates cannot touch, and then you just take them and you roll it up and you get a nice little concise thing. All right. So what is the function of a dielectric? Well, first of all, it solves the mechanical problem of having two large plates very close together but not touching. Remember, there's going to be an electric force between a positively charged plate and a negatively charged plate, but we can't have them touch. If they touch, then we no longer have a capacitor because the charge will just transfer. So that putting a piece of mylar or Teflon or some type of insulating material in there will keep the positive and negative plates from coming in contact. The second thing we have to understand is any dielectric will eventually break down when exposed to a strong enough electric field. Many insulators can tolerate stronger electric fields than air. Okay. One example of dielectric breakdown that you're very familiar with in a way is a lightning strike. Here's how lightning happens. Up here in the cloud, you get a buildup of charge, and it may be positive or it may be negative. Let's suppose that the charge has accumulated a positive charge, because I do positives. So here's the bottom of the cloud. It's very positively charged. Down here, here's the Earth. Remember, the Earth is essentially neutral. But if there's a strong positive charge above it due to this cloud, then it will accumulate negative charges. So we've got a cloud, we've got the Earth. If I have positive charges on the cloud and negative charges on the Earth, this looks kind of like a capacitor. It has an electric field that points away from positive towards negative, so here's the electric field. Now, if the charge on the cloud is small, nothing's going to happen. But when this charge builds up really big, we're going to get a lightning strike. All of a sudden, kabam, and we have electric current flow from the negative current flows through the atmosphere, through the air, up to the positively charged cloud, or vice versa. And you go, well, how does that happen? It happens because the air becomes ionized. When the air becomes ionized, that's dielectric breakdown. In other words, the air allowed current to flow. The lightning strike is a large flow of electric current through the air. So, when the lightning strikes, air becomes ionized. What does that mean when I say it's ionized? I mean it now has negatively charged and positively charged things. Some of the electrons are literally ripped off of the atoms. When you start pulling electrons off of atoms, you get positively charged ions in the air, you get negatively charged electrons, and you get a flow of electricity. That's dielectric breakdown on a large scale. Okay, so if you have a circuit and you have a capacitor that's supposed to store charge and store electric energy, you don't want current to flow through it. When you get dielectric breakdown inside a capacitor, it'll look like a hole got burnt through it, because literally a spark of electricity went from the positive plate to the negative plate, and it will literally burn a little hole in that dielectric. Okay, any dielectric can break down if you have a strong enough electric field, which basically means a high enough potential difference between the plates. But a lot of materials actually will hold up better than just plain air. So putting something in between there can help prevent that, what would essentially be a short circuit in the capacitor or a dielectric breakdown. The third thing that it does is dielectrics increase the capacitance of a capacitor. Compared to a vacuum or air. The dielectric qualities of air are very similar to vacuum, not quite as good, but they're very similar. But if we can put in an insulating material, we will actually, what that basically means is the capacitor can store more charge at a lower voltage. How much more charge it can store was going to depend on what type of material you use as a dielectric. So dielectric materials are rated by something called a dielectric constant. The dielectric constant we use a real special symbol called a capital K, good for constant, is simply the ratio of the capacitance with the dielectric compared to the capacitance in a vacuum. So C is the capacitance with the dielectric, and this is with the capacitance in a vacuum. Some of our common dielectrics, the ones that probably are Teflon. Teflon has a dielectric constant of about 2.1. So it'll let you store a little bit over twice as much charge for a given voltage. Mylar, I know you've seen those Mylar balloons. Mylar has a dielectric constant of about 3.1. And PVC, polyvinyl chloride, used to make pipes and things, has a dielectric constant of about 3.2. There is a material called strontium titanate that has a dielectric constant of 310. So almost impossible for that to break down. So why does putting in a dielectric allow it to hold more charge? So let's see what would happen. Let's think about if we have a regular parallel plate capacitor. Here's the positive plate. And we're going to sandwich some stuff in the middle here. Whoops. And here's the negative plate. And I put a dielectric in the middle. I put in a layer of something. The charge in the dielectric, now remember, the dielectric is essentially an insulator, but it doesn't mean it won't have some slight charge motion. What's going to happen is there will be some negative charge on the dielectric that will move towards the positive side. And on this side, the molecules will shift enough. It's not going to be like a conductor where you have mass migration, where you'll get some small, I probably should do what? I'm not going to put quite so many. Let's just erase some of these. You're going to get some negative charge. And on this side, you're going to get some positive charge. So this slight amount of charge in the dielectric is going to reduce the value of the electric field, and it's going to reduce the potential difference. In particular, the voltage, whoops, with the dielectric, the voltage will reduce, so it's smaller by a factor of K, and the energy stored will also reduce. So it is smaller by a factor of K. So it would, not the energy, I said the wrong word, the electric field. So the voltage and electric field strength are both reduced by a factor of K. Let's do a problem. Let's start with an air-filled capacitor. An air-filled capacitor we treat the same as we treat a vacuum-filled capacitor. There's not a lot in the middle. This air-filled capacitor has an area of 2.00 times 10 to the third square centimeters. It has a plate separation, D, of 1 centimeter. It's a fairly big device. And it's got a voltage across the plates of 3 kilovolts. A kilo is 1,000, so this is 3,000 volts. All right. It says the capacitor is removed from the power supply with no charge loss. Sheet of insulator is placed between the plates and the potential difference, V, drops to 1.00 kilovolts. All right, let's do some work. First question. What is the capacitance and the charge before and after the dielectric is inserted? Okay, well first let's look at what the capacitance is without the dielectric. The capacitance could be found using epsilon naught A over D. So I have 8.854 times 10 to the negative 12. The area is given in square centimeters. It's 2,000 square centimeters. So I have 2,000 square centimeters. And I need it in square meters. I know 1 meter is 100 centimeters. So I'm going to have to square that to get rid of that centimeter squared. So actually I'm going to end up dividing by 10,000 there. So that gets the area. And the distance is 1 centimeter, which is 0.01 meter. So that came out to be 1.77 times 10 to the negative 10 farads. I'm just going to leave it like that. I could change that. If I wanted to say, oh, let's go 10 to the negative 12, that's a multiple of 3. That's 100 times smaller. I could make this 100 times bigger. So another answer could be 177 picofarads. But I'm really okay with just leaving it 1.77 times 10 to the negative 10 farads. If I want to get the charge, I know I have a 3,000 volt potential difference. I know C equals Q over V. So the charge is CV. So 1.77 times 10 to the negative 10 times 3,000 volts. And I get that the charge stored is 5.31 times 10 to the negative 7 coulombs. Again, I'm going to leave it like that, but just in case you're ever asked to answer a particular way, again, I could make this 10 to the negative 9. That's 100 times smaller. That would make this 100 times bigger. So I could answer that as 531 nanocoulombs. All right, let's keep going. What about after? That was the before. Well, we know the capacitance, the new capacitance is K times the original. So, we don't know K, do we? Nope, let's not go there. Let's take, what do we know? We are asked to find the charge before and after the dielectric is inserted. Well, I know that afterwards, the capacitance is equal to, Q over V. The charge on the capacitor did not change. Remember, it says that it was removed from the power supply with no charge loss. So the amount of charge, 5.31 times 10 to the negative 7 coulombs, has stayed the same. The voltage, however, has dropped to only 1,000 volts. That's going to make the capacitance of this 5.31 times 10 to the negative 10th farads. Notice it essentially tripled the capacitance if you're comparing these two. So the charge is the same before and after. So as far as the charge after, it is still the original 5.31 times 10 to the negative 7 coulombs. So we had no change in charge, but when we put that dielectric in, that potential difference dropped from 3,000 to 1,000, effectively increasing capacitance by a factor of 3. So part B says, what's the dielectric constant? Well, the dielectric constant K is just the ratio of C over C0. So in this case, it's 5.31 times 10 to the negative 10 divided by 1.77 times 10 to the negative 10, or 3.00. Notice the dielectric constant does not have any units because it's simply a pure ratio of farads to farads. The last question says, find the electric field before and after. Well, for a parallel plate capacitor, the electric field is simply the voltage divided by the plate separation. So initially, we had 3,000 volts, and we had a plate separation of 0.01 meters. Dividing by 100, that's like multiplying by 100. So that's like 30 or 300,000. We get 3.00 times 10 to the 5th volts per meter. That's the before. Afterwards, when we put that dielectric in, it reduces the voltage. And so if we wanted to, that would be for the vacuum. And by reducing the voltage, it reduces the electric field. And we get 1.00 times 10 to the 5th volts per meter. Okay, that concludes all the videos in the main portion of the notes. I do want to work lots more examples on all of this during our class time together.